Hello again. Today's lecture is going to be basically how we can now put all these different blocks together of analog plant, digital controller, A to D, D to A, all of those blocks. How do we put them together in both open loop and closed loop configuration to make it a genuine closed loop or digital control system that you're going to be dealing with in your projects and in your homeworks and so forth. So let's go to the slides or the book. And this is actually the lecture of today is based on the second textbook, chapter 4 of the book by Philip and Haber, and this is the open loop discrete system. So basically, we want to first describe to you the difference or the relationships between a function of Z and a star function of S. You noted that if a continuous signal goes into a sampler, the output of the sampler is a starred quantity. So let's consider let's say a Z transform of a function E of K, which is called E of Z. It's going to be an infinite series of terms which have different values of the function at sampling points 0, 1, 2, and so forth, multiplied by powers of Z, starting from Z to the power of 0, then minus 1, minus 2, and so forth. And if you store that quantity, original value, original one, it would become basically E0, E of T, which is the value at the sample 1T, and Z minus 1 is actually E to the minus TS by definition, and so forth, so on, of E to T, E to the minus 2T, and so forth. So these are the basic relationship expressions of both EZ and E star S. So therefore EZ is really is E star S when you replace when you apply this relationship, Z equal to E to the ST. So for example, looking at an example here, you have an E of S, some function which has 2 poles and no zeros. There is a very powerful table, Z transform table, in Appendix 8, the back of this particular book, which you have access to it on Dropbox. This book is already on Dropbox, as we said in the previous lectures, and you can always get a copy of this and put it handy in your to access you for your homework and your later on midterms and so forth. So corresponding to this expression, you get this E of Z right out of the table. And now from that, E star is basically applying Z equal to E to the ST everywhere, which is what you see here. Okay, so that's how you compute E star and EZ from an original ES. There are 3 different functions here: function of S, function of Z, and a star function of S. So this particular book goes into a lot of detail of how to solve a discrete time system, or how to solve a discrete time equation, and including residual functions. I'm not going to confuse the class with so many different approaches. Instead, I only picked the one which is the most powerful one, and that is partial fraction expansion. For example, if you have an E of Z here, looking like this, and you want to invert it into discrete time, you bring a Z here down below here, EZ over Z, then you have this expression do partial fraction expansion of this, and then go to the table and come back. That's how you do that. And that's the most convenient way. All you need to do is to refresh yourself how to do a partial fraction expansion in an algebraic form. You're supposed to have done it in your Laplace transform formulation in a first control class. So we'll skip that, but we do know from last lecture that going from a sampler to a sample and hold to an analog plant, you actually have an expression of 1 minus e to the minus t st divided by s. This is the sample and hold transfer function times the plant transfer function. So if you look at let's say figure 4.1, which is here, here's your sample and hold, this is your plant, and we call this to g of s. And then that part A changes to part B. Okay, this is a typical open loop sample data system. Of course, when you want to look at E of z, which we'll do it in a minute, 1 minus e to the minus st is already 1 minus z to the minus 1. So that can go away, and then what's left is gp over s, which you have to convert that into a z transform formulation. Okay, so in this particular situation, your output C star is going to be GS, which is this, C star is going to be GS times E star. Okay, it's very simple. Input to this block, which we call G, is E star. Once you get an E star or some function star going into a block, the output is also going to become a star quantity. It's going to be S quantity, but we will start it after we express it. So here is your C of S, equation 4.5. We assume that C of t is continuous for all sampling instants, because if they are not, you cannot even do sampling. So starting this will give you basically G star, E star. And this quantity right here, which can be expressed in this fashion through infinite series, you have, once you have a combination of a non-star and a star quantity, when you start quantity, then a star will go to both of them simultaneously. So this will become G star, E star. Okay. On the other hand, if a star was not here and you just had G times E, then you have a star only the product of those two terms, not the individual ones. You have to remember that a star is a funny situation. If they are not present, then the whole function should be a star. We'll see that more and more in a few minutes. So in any case, we basically then go from that C star equal to G star, E star, and they immediately go to equivalent GZ, EZ, and GZ. So the output of the open loop system, that sample data system shown in figure 4.1, is simply EZ GZ. GZ is called the pulse transfer function, and is the transfer function between the sampled input and the output of the sampling instant. Okay. And let's now look at an example. It is the best way to explain what's going on. Assuming that you have a function of S, A of S, which is going to be 1 minus e to the minus ts over s plus 1. The plant is 1 over s plus 1. What you have here is a G divided by S, which is this quantity, times this, the numerator portion of the sample and hold transfer function. So if you look at 1 over S plus 1 as B sub S, this particular function, for example, f of star 1 minus e to the minus st, as we know, is 1 minus z to the minus 1 from here, which is also shown as z minus 1 over z. This part is going to be multiplied by the z transform of this, to give you the z transform of A. So you go to, again, z transform table, you look for expression of 1 over s times s plus 1. If this expression is already in the table, you don't even have to do partial fraction expansion. If it's not, then you have to do partial fraction expansion of this, bring it to a combination of factors where you can immediately go to the table and find equivalent z transform. So in this particular case, it was available in that z transform table at the end of Philip and Haber's book, second textbook, which is this quantity. So now if you multiply this quantity with this z and this z minus 1 cancel. Right? This z minus 1 and z minus 1, and this z cancel, and that's what you get. And you can see this is a simple transfer function which has a pole at plus e to the minus t. And for all the positive value of t, which they are, e to the minus t is smaller than 1, then it's going to be pole inside the unit circle. Now let's look at figure 4.2, which is shown here. Again, you have that same system I showed you, and the sample and hold. If you plot the response with the unit step, you get this. You have unit step function, and all the sample quantities are shown here. In your simulation on MATLAB, what you get is those dots. Okay? Then you can sort of interpolate it as an exponentially approaching function to 1. Okay? Which is similar to what you already know in the analog system. So the solution of this, after you go to the z transform table, z over z minus 1 is the unit step, so that's number 1. Z over z minus e to the minus t is basically e to the minus nt. So it's 1 minus e to the minus nt. Equivalent to this, for the continuous term c of t would have been 1 minus e to the minus smallest t, lowercase t, e to the minus t, which gives you the entire function. But this particular function only gives you those dots, those sample quantities. All right. So now, let's see what else I need to cover. Going to the notes here.
Use the bindings because the mouse is not visible.
Yeah. Okay, and basically, this is what I just told you, e of t, 1 minus e to the minus t. Now, one thing that you want to, for example, check the final value of this function, final value of this function when t goes toward infinity. We know the answer is 1, but let's check that. So, to do it, you go look at e of z, which is e of c of 0 there, which is this function right here, or this function right here. We want to basically find the final value of this. We use the final value theorem in z transform. The final value is going to be a steady state value of c is going to be limit of z minus 1 times c of z as z goes to 1. And that is going to be the limit of z minus 1, gz, ez, and then you put GZ and EZ here. This Z minus 1 and Z minus 1 here cancels, and then you have basically Z times G of Z. But when Z equal to 1, this is 1, then you have G of 1. Okay. And this is a DC gain of the system that are defined by this value. Okay. And for example, the above, it's going to be 1, because if you remember here, when Z here, when this is 1 and this Z minus 1 disappears, in this two term right here and here, right here and here, if Z equal to 1, then 1 minus e to the minus t divided by 1 minus e to the minus t is going to be 1, which is what you have here. Okay? So it checks precisely what you expect it to be, and that's your final value of the function. So DC gain of any system transfer function would be the limit of Z goes to 1 of G of Z. Okay, now let's now look at a bunch of potential combination of blocks. Let's look at this function, then I'll move back and show you what this is trying to do. Here you see two samplers and two blocks, G1 and G2. So what is going to be C of Z? C of S, rather. C of S is simply G2S times A star. Okay. And what is A? S is simply G1 times E star. Those are the expression that you have. So for that part A, C is going to be G2 times A star. And then immediately from there, since you have one star, one non-star, then if you star both of them, you get G2 star, A star. A star of A is the same as itself. Remember that. When you sample a sample signal, you get the same signal back. This is consistent. So this is C of Z, therefore it's going to be G2 of Z times A Z, where A S is G1 E star as you saw before, and A from here, AZ is G1 Z E Z. So that is all relevant to part A of that set of blocks. Now let's look at this block. This block, unlike the other block, has no sample in between. So C is going to be G1, G2, E star. And then when you want to get C star, you have to multiply G1S by G2 together as two functions of S, then star the resulting quantity. So the part A, therefore, is going to be, oh, I'm going too fast. Okay, part B, therefore, is going to be, okay, that's for part A. So part B here, C is going to be G1, G2, A star, which we said before. And if you want to find C star, is G1, G2 quantity star times E star, which is shown in this fashion. In equivalent Z, after that C star Z becomes CZ, G1, G2 star becomes G1, G2 together, Z, function of Z, times EZ. That's how you interpret that. So later on, when you are asked to simplify this block, you have to go through this mechanism, this argument, and just be careful how to deal with the star quantity. Okay, now let's look at part C. In part C, you have two blocks. In between, you have a sampler, but you don't have any sampler for the input, unlike the part A. So what is this now? In this case, you have C is going to be G2 times A star. And AS is going to be G1 times E. Okay. Then in that case, when you want to compute A star, both G1 and E together has to be multiplied to be a start quantity. So you will get for part C, which is here, CS is going to be G2 times A star, but A itself is G1E. Okay, and then that has to be a star together, right here. Because there is no sampling here, E and G1 has to be multiplied together as one combined signal. And that combined signal is now being started here, and there will be Z transformed here. So CZ is G2Z, G1, E together of Z. Okay? So therefore, you can see that you basically have an easy way, really, if you think about it, it's an easy way to find the equivalent G of Z of the function. So the authors here have a section on open loop system containing digital filters. These are really not part of the course because this is goes into the overlaps with digital signal processing. So you can, for example, here you see a picture of a space shuttle, which there are a ton of digital control system all over the place, in joints and in all the various sensors. One time, one of my former PhD students who was actually later on became a colonel in US Air Force, he tried to model the entire model of a space shuttle. And it's a huge, basically infinite dimensional system, because a lot of portions of this structure are flexible. And flexible parts of any system cannot be defined precisely with ordinary differential equation. They have to go to partial differential equation, which gives you infinite potential equation. Therefore, that is a very large scale system, which if you reduce it, it becomes 200 state variables. So, but in any case, digital filters locate in a box of digital controllers. So you could think about a digital filter as a digital controller per se. So let's suppose that you have a digital filter here. The Z transfer of the output is going to be equal to the transfer function of the digital filter times the transfer function of the signal E. If you start this quantity, you will have M star is D star times E star. Now, what you basically see, because of this analog to digital converter, that a star quantity can therefore be segregated to both of them. So, therefore, you could look at the fact that putting a digital to analog converter, the output of that converter, M bar, is going to be 1 minus e to the minus st divided by s, which is your digital to analog converter, times M star. And here then you have a plant, analog plant, GP, and GP output is going to be GP times M bar. And GP times this quantity we saw before, and if you look at the value of M star in terms of D and E, you get this expression for the output, which looks a bit messy, but once you move them into Z domain, it becomes very simple. G, D, E, each of them a function of Z. So therefore, from here to here, all you need to remember that you have a E coming in time and S, it becomes EZ. You have a D of Z here, and you have a C of Z here. Okay? Just like that. Okay, and we now let's look at, for example, a more analytic example for this digital filter. We want to find a step response of that system you just saw. Suppose that the filter is described by a difference equation here. This difference equation is basically an algorithm which you code to represent your digital filter in a digital environment. It takes upon two samples of E and multiplies the one by 2, subtract the other. If you do the M over E, you basically have a 2 times Z minus 1, because basically this would give you M of Z is equal to 2 E of Z minus Z minus 1 E of Z. That's what you get if you take Z transform, skipping a step that the authors have done. You calculate D of Z, M of Z over E of Z, 2 minus Z minus 1, which if you bring this as the 1 over Z, you become 2Z minus 1 over Z, which what you see, the digital filter has a 0 at 1/2 and a pole at 0. Now assume you have the old plant 1 over S plus 1 for GP. Then from a previous example, you basically pick up the sample and hold portion and S plus 1, and you take care of Z minus 1 over Z for this portion, and then you go to the table and you simplify it, you get this expression for Z transform of GP. So now you have your G here, which is this quantity, and you have your digital filter here. So as you saw before, for a step input, you have this kind of expression for E. C is going to be D times G times Z, E like before. This one is 2Z minus 1. G, we just computed it. And of course, E is this, Z over Z minus 1. Then this is going to be your answer. Okay? And you have 2Z minus 1, 1 minus E to the minus T. Then this Z and this Z cancel. You have Z minus 1 and Z minus E to the minus T. So now, for the overall open loop system, which is what you have right now, you have a pole, a 0 at 1/2 with the constant here, a pole at plus 1, and a pole at plus E to the minus T. Okay, that's what you have. Now, if you want to find C of T, as I told you before, don't go to residue and others. I don't want to confuse you. Just go to partial fraction, like here. Bring that, put this Z here, C of Z over Z. Sometimes that Z appears in the numerator, you bring it to here. But in this case, it doesn't appear, but you just put it here. You have Z both sides. So now you have 2Z minus 1 times this, divided by Z times Z minus 1, Z minus E to minus T. And you do partial fraction, you have 3 terms, 1 over Z minus 1, 1 over Z minus E to minus T. Here, here, and here. Now you're ready to go to the table. 1 minus E to the minus T over Z. 1 over Z is really just a constant, which is this. It's a pulse function. A pulse with this kind of amplitude. 1 over Z minus 1 or Z is going to be it's actually going to be Z. Let me backtrack. C of Z is going to be this quantity times Z. Remember that Z has to go here. So when it comes here, it cancels this one, it becomes 1 minus e to the t. And then here becomes Z over Z minus 1. And here it becomes e t minus 2, Z minus e to minus t, quantity times Z. We lend Z to the left side, now we bring it back to the right side. So now, this particular term is actually like an impulse. For one single value is non-zero, for everywhere else is actually 0. So this is going to be equal to 1 minus e to the minus t. This z over z minus 1 would be another 1, and then this quantity times e to the minus nt. So this will become, now notice what you see here, the authors have played a trick on you. They eliminated n equal to 0, which is what this value is. So starting from 1, you basically have 0 for this portion. For this portion you have 0, because this is an impulse function, which is only defined at n equal to 0. Therefore, at n equal to 1, you can ignore that. You go from here to here. 1 plus e to the t minus 2, this quantity is e to the minus nt. However, now if you find the c of 0, the initial value, when n is equal to 0, you get 1 minus e to the minus t plus 1. Here you have e to the 0 is going to be 1, et minus 2. So you have 1 plus 1 minus 2, 0, minus e2 and plus e2 is 0. And that's what you have. So anytime you are told to find a solution of a system or a difference equation, you do have some initial condition. At the end, check the initial condition to make sure you have the right answer. Okay, and that is really a very important check at the end of your calculation. So now, let's look at modified Z transform. Again, is out of the outline of the course. This is Z transform where you have multiple of actual, you have a delay attached to the Z quantity, and in gradual level of this course, that subject may come in. You see, they call modified Z transform. This is what came out from the work of my mentor, Professor Eli Jury of UC Berkeley and University of Miami. So you have Z comma M, where M is a replacement for the delay delta replaced by 1 minus M. Again, don't worry about those part. This is not, you're not going to be, again, with system with time delay, we will cover it later on toward the middle to the end of the course. And let me go to let's see. Yeah, let's go to next subject. Again, non-synchronous sampling is another one where the samplings are not equal. That also is a more advanced function discussion. Let me now go to the subject that I ended my last lecture with you. Basically wanted to find the equivalent of the state equation and output equation from a continuous function to a discrete function. So we have 4 matrices from continuous function. We want to find the equivalent 4 matrices in discrete function. You need to also note that in reading those 2 textbooks, you are confronted with slight changes in notations. In the in the book by Franklin and others, A would have been a capital Phi in Greek, Phi, and B is a capital lambda, and this is H, and this is J, capital J in English alphabets. But don't get confused. As long as you know what you are doing, you can choose any notation you like to do. So, in order to find the state, remember we put those simulation diagrams in the last lecture, and we discussed two different simulation diagrams. One was controllable canonical form, one was observable canonical form, and both of them gave you respective state equation and output equations, and they were dual of each other. A matrix of one was the transpose of the other, and so forth and so on. But the ultimate goal is to how do you find the state variables model? That's what you want to learn. So to find the state variable, you go these steps. Like we did in last lecture, there are a simulation diagram from the Z transfer function. Label each time delay output as a state variable. Okay? Write a state equation from the simulation diagram. Very simple. So, in continuous time, you draw this in S domain, S transform, and you label each end of the integrator rather than time delay. Every integrator would be output, it would be a state variable. Then you write a state equation. Now, let's stay in discrete form. For example, you look at figure 4.16a, which is this. You have a discrete controller here. You have an analog plant with a D2A sample and hold function, and then you have a sampler for your input. So what we want to do is to basically rewrite this in a state equation. So that will be of G of Z, which you already obtained from previous example. D of Z also you found from the previous example. A simulation diagram is shown in figure 4.16b. D 2z minus 1 over z is this. 2z plus z to the power of 1. Because if you divide this by this is going to be equal to 2 minus z to the minus 1, or 1 over z. So you divide it into two additional quantities, and this is what they are, right here. 2 plus or minus z to the minus 1, which is the same as 2z minus 1 over z, okay? And then you have here, you have 1 minus e to the minus ts over s, and then as you remember in your g of z, you have 1 minus e to the minus t divided by this. So this quantity is just a constant. So we just leave it in the middle. And then 1 over z minus e to the minus t is easily represented by one delay with a feedback of e to the minus t. So the input here is going to be 1 minus e to the minus t added to e to the minus t times x1, and that will be this portion right here. So with this, now with this situation, you have two state variables. x1 output of this delay, x2 is out of this delay. And then your equations are going to basically look like this, right here. X of k plus 1 is this matrix A, A11, A12, A22, and A22. And then you have a B matrix, which is B1 and B2 here. By combining those two, basically by just reading off the here. So X2, K plus 1 is going to be E, okay? And that's what it is. X2 k plus 1 is just going to be E right here. E. And then x1 x1 k plus 1 is going to be 1 minus e to the minus t times this quantity, but this quantity is 2e minus x2. So bring that as an input to this, you add it to x1 times e to the minus t, you get these expressions. Okay? It's really that simple. You just need to be careful how to go from these quantities to the simulation diagram and then just calculate algebraically the input-output relationship. So that's, and then of course the output y is just simply x1, 1, 0, x. Nothing to do with e. E, there is no d function. No, e has no influence on y directly. So that is how you do a state variable for a discrete function. Now again, give you a quick review of continuous time discrete function, continuous time state variable. Suppose you have a system x double dot equal to f, and you define x is the displacement or position of a mass, and F2 is applied force. It's just like a simplified version of your shock observer of your car. Okay, that's what that is. And here you assume that the position is going to be x of t, which is your state variable v1 position. A state variable v2 is the derivative of the v1, which is x dot. Now, when you want to write the state equation, x1 dot is v1, which is equal to x2. Okay? v1 dot is equal to, or v2 rather. I'm sorry. x1 dot is v1 dot and v1 dot is v2. v1 dot is v2, right here, 1 times v2. 0 times f. And v2 dot is x double dot, which is equal to f of t, just directly equal to the force. So you have nothing here, 1 here times f of t. And that's what you get here. And later on we will show you that this system, as simple as it's shown, it is basically, I think I described that last time in the previous tape lecture, is this expression right here is the attitude of a satellite control system. It's one of the three dimension of the controllers for the holding a satellite on the orbit. And this combination of A matrix and this B matrix we will show you later on, which looks very sparse, but they're actually controllable, which means you can't find the control for it. Okay, let's now, that will be your continuous version of your state variable. Let's now look at a more complicated system. We have a figure 4.17a, a mechanical system, which is a more like really accurate representation of a shock observer in your car. This could be actually, this portion could be a shock observer. This mass is the mass of the car and the tire, and somewhere here you have a friction of the road, connected to the road, so this will become like a shock observer. And never mind this signal flow diagram, these are out of really picture for many control system. We don't cover it in the first control class. I'm sure you have not seen that before. In the old days, when I was a control engineering student, we were dealing with these because we didn't have MATLAB, we didn't have a lot of software available, and we didn't have a digital calculator, we were basically had a slide rule, and we had to do a lot of things by hand and look at the loops, the number of loops, the number of nodes, and so forth, come up with a transfer function. But don't worry about that. All I want to do right now is to go directly from this system and write the state equation for it. Now, what you see here is that a spring holds energy into it, stores energy in it, and that should resemble for you inductor which saves magnetic energy in it. The mass M has potential energy if it displaced from its location y1 to some other location, and this mass is analogous to a capacitor in analog circuits. And this dashpot, or this friction term, dashpot, which basically absorbs energy, it's resistor. So you and this force could be, this force right here, this force here could be basically coming from the road into the shock absorber. You go into a ditch, or you go into a particular, let's say, a place where you have to go over the hump, and you see some on the road to reduce your speed. Don't speed too much in a small, for example, communities. Anyhow, this force is equivalent to some, for example, current source in analog circuit device. In order to write the differential equation for this mechanical system, you go to Newton's law of gravity. Force is equal to mass times acceleration is equal to all the forces combined. So here you have acceleration of the first mass, y1 double dot. It has to be added with the friction force, the friction constant times the velocity, times the energy of the spring, K times Y. You may remember, or may not remember, there's a law called Hooke's law, which shows the force absorbed by a spring is a spring constant times the displacement. Then what you see after that there is an interface here, B2, between M2 and force. So there is a B2 times Y2, Y1 minus Y2 dot, B2 times Y1 minus Y2 dot. All of these are forces acting on the mass M1, which is now considered to be equal to 1. Made it simple. So it's 1 times Y1 double dot, mass times acceleration is equal to all of these forces. Then for Y double dot, for the second one, Y2 double dot, working on this mass, which is also equal to 1, is equal to F plus B2. Now this time Y2 dot minus Y1 dot. That's the interface between the two, connection between the two. So here is what you have, is equal to Y2 double dot plus this is equal to external force. Here you didn't have external force, so U is equal to really F here. U, T is the force here. Okay, so now you have two ordinary differential equations. What you first need to remember and look for, how many dots do you have in these equations? What's the maximum number of dots you have? In that first equation you have 2 dots maximum. Second equation, 2 dots maximum. Therefore you have 2 plus 2, you have 4 state variables. Here they are. The 4 state variables are y1 y1 dot, y2 and y2 dot. One position, one velocity. Second position, second acceleration. I'm sorry, second velocity. Okay, so the two positions and two velocities are your non-unique candidates for your state variables. Therefore, you expect your A matrix in this equation, your ASC matrix should be 4 by 4. Your BC matrix, you have 4 by 1, U is equal to 1, only 1/4. The output is going to be defined, maybe y1 is equal to y1 and y2 is equal to y2. Those are the two outputs, which is going to be looking like this, 1 and 1 here. And these are basically coming directly from the 4 state variable. V1 dot is V2, which is 1 times V2. V3 dot is V4, 1 times V4 all the way down below here. Then the other two are direct expressions for this equation and this equation. And you just plug in for y2 dot, for example, x2, y1 dot x1, x2 is x4, and so forth. You just replace these y's by respective v1s. Okay, I'm sorry, I keep confusing myself. The state variables are v's, not x's. v1, v2, v3. For example, if you rewrite that first equation, y1 double dot is going to be v2 dot. y1 dot is going to be b1 times v2. K times y1 is k times v1 plus b2, y1 dot is v2 minus y2 dot, which is v4. That's how you do it. You get rid of all the dots except one, and that's going to be the one on the left side, right here. And here, y2 double dot is v4 dot. y2 dot is v4, and y1 dot is v2, and that's what's going to give you this value right here. You have b2 times v2 minus b2 times v4 minus b2 times v4 right here. Okay, that's all you did, and now you have the A matrix, the B matrix, and a C matrix. There is no D matrix. So this is how you do a state variable for that mass spring dashpot mechanical system, which is really like an RLC network in our electrical engineering. Resistor, inductor, capacitor. In this system you have two capacitors, two resistors, one inductor, and a current source. That's what you have. These equations are the same for those circuits as well, except that B1 would be R1, R2, and this would be L, and so forth and so on. And then C is, the capacitors are assumed to be 1. They don't show up. Okay, so this is what you have here. Now, what we want to describe to you is how we can go now from a state equation to Laplace transform. If you take the Laplace transform of this equation and this equation, you have S times V of S minus V0, the initial condition, equal to AC, V of S plus BC, U of S. If I collect these two together and collect it, becomes S times identity matrix, because S is, remember, S is the scalar. AC is the vector quantity, n by n. I cannot subtract a scalar quantity from there. In order to do that, I multiply by n identity matrix. I times S or S times I minus this. Inverse times V0 plus IS minus AC minus this. So we define a phi matrix to be the inverse of Laplace inverse of this quantity. And later on we call that state transition matrix. Okay. So the solution for V of t is going to be described by a homogeneous part, which is going to be the transition matrix times the initial condition coming from this portion of the Laplace transform inversion. And this inversion is going to be a combination of one S function of S times another function of S. What is that? That's a convolution integral. If you remember the Laplace transform table, if you have a combination of two functions of S, you pick up a convolution integral like this. Okay. So this is called in mathematical differential equation, this is called particular solution. This is called homogeneous solution. Okay, which this function in open term is going to be like this, but it more precisely you can every element of that matrix here can go to a Laplace transform table and calculate it. For example, let's look at this example of figure 4.18 here. We have x1 dot is minus x plus u minus x dot, and y is equal to x dot. So here it is. x1 dot is equal to u minus y, which is x dot, minus x. So that's what that is all about, that function. And then y is equal to x dot, as you see, just directly from the simulation diagram. Okay, and then these equations are not in a standard format for a state equation, since x dot appears on the right side. You see, right side. Anytime you have a dot quantity on the right side of a state equation, it tells me that you don't know what you are doing. It all has to be on the left side. Okay, and therefore we move that on that side and we solve for it. It becomes minus 0.5x plus 0.5u. Now this is a state equation. That one is not. This one is okay, because you can replace x dot by this quantity, and the dot here disappears. And therefore, you now have a situation here where your output is going to be equal to minus 0.5x plus 0.5u, which directly replacing this quantity. Okay, now what we now have is that okay, we got this part, and we now present a procedure for writing the state equation in the standard format in this figure. So we can redraw the simulation diagram of 4b into this form. Now we write the equation for x dot and y in terms of the input of the diagram, xt and ut. So we have x dot is equal to x minus x, u minus x dot, which now is equal to y. So we now have a formulation here which makes sense, and so forth. In other words, once you come up with a state equation coming out of one simulation diagram, and if that simulation diagram doesn't look standard like is described here, you can use that expression and write it in the form of a basic Laplace transform. What is missing here is an integral function here. That block belongs there. There is a mistake in the scanning of this page, of that text page. Okay, so in any case, now what we basically want to indicate to you, now that we know that solution of a continuous function is going to be a combination of homogeneous and discrete, what you do if you want to find a discrete state equation like this, what you do, you solve the continuous time for only one sample. Go from kt to kt plus t. And the resulting transition matrix is your state matrix in discrete form. And that discrete version of your convolution integral will become your B matrix. So these two, this function are part of a MATLAB command called C to D. Let me basically show you. This is continuous, and we want to find the discrete. Here is a continuous matrices. You go from a state space to transfer function. It gives you the numerator and denominator of your continuous function. You put that in with the sampling value sample. You go to continuous to discrete. This function is basically that development that you see above those pages. I described to you briefly. The A matrix of the discrete version is equivalent to the state transition matrix of the continuous function evaluated at one sample. And B matrix is going to be defined by that integral I showed you before. Now that you have the discrete version of your matrices, C and D does not change. So you give it to a state space to transfer function, and you get a numerator and denominator in Z transform. This is Z transform, this is Laplace transform. So you can see all these pages that I described to you, maybe 8 or 9 pages of textbook, you can do it in 3 lines with MATLAB. Okay, which is really an amazing tool in your hand, which in the 1960s I had no idea about that. Okay, so let me now close this session, and you can in this lecture, which we are cutting it a little bit short, because Mr. Majumdar Abhijit will spend about 5-10 minutes with you folks to guide you toward a successful implementation of your projects. You already have visited AceLab, and you have presumably already teamed up with your mentor in the AceLab. We have several different projects. Abhijit is involved in many of them. We have a driverless car, and we have many other robots, track robots, and so forth. Lots of things you can do. And in this lecture, we looked at open loop system, how they conform in the typical sample data system, how we treat a star function and Z function and S function, mix them together and try to basically remember where you have a sampler in the loop of your system. So far we only looked at open loop system. Our next lecture will be on closed loop system, which makes even more realistic as your potential digital control system. Thank you, and see you soon.